Hi everyone, this is Team 10 and we're going to talk about our autonomous racing car project.
Hi, I'm Alex and I'm going to talk about the car design. This is our car design. The PCB was designed by me and soldered by Tommy. The Jetson Nano is powered by two 5 volts from the PCB, and the PCA and OpenMV is powered by one 5 volt from the PCB each. Since the motor needs to be ran at 1K to 2K Hz and the servo at 50 to 100 Hz, while the PCA could only have one frequency value, we had to use the OpenMV2. We set the frequency of the PCA to 100 Hz for the PWM signal and the servo and the OpenMV to 1.5 Hz, 1.5K Hz for the PWM signal of the motor. We found out that when the camera was lowered, our average angle that was detected by the camera was not stable, which would make the car shake a lot and it would be hard for us to tune the PID. So we made our camera tall. We also found out that when the car is running, the LDOs and the transistor can get really hot, which would affect the car's performance. So we added heat sinks to them. So that's it for the car design. I'm going to hand it to Hui to talk about our algorithm.
Hi, I'm Hui. I will tell you how the car can actually do lane following.
Our algorithm for operating the lane following car revolves around the concept of the average angle. When the average angle is zero, the car remains on the correct track. If the average angle deviates from zero, we adjust the steering wheel to realign it. To achieve this, we employ Hub-like P for angle detection, allowing us to fine-tune the values by calculating angles based on 2 points x1, y1, and x2, y2, and averaging them across all line segments. We obtain the average angle. To ensure stable car movement, we have identified an issue with our servo hardware, which causes the car to have limited left turning ability and slower response time compared to right turns. To address this problem, we have modified the PD controller. Instead of using a single set of parameters KP and KD for both left and right turning, we now have separate parameter pair for each direction, resulting in a total of 4 parameters that require turning.
Let's see for algorithm. Right now, Tommy will talk about how we can come over the issues.
Hi, I'm Tommy. Right now I'm going to talk about how we overcome the obstacles.
During the design phase of our autonomous racing car, we encountered various challenges that require innovative solutions. Initially, we discovered that we had placed the LDO and transistor in the wrong place, which led to the burnout of our circuit. Then, we faced instability in acceleration and cruising speed due to overheating issue with the transistor and the LDO. To address this, we successfully remade another PCB and implemented heatsink to these components, effectively mitigating the problem. As we proceed with the test round, we discovered that the camera angle played a critical role in lane detection. It became evident that detecting the lane at the farther distance compromised the car's stability during turns. To rectify this, we designed a 3D printed camera support rod extending the height of the camera. This adjustment allows us to detect the lane precisely beneath the front wheels, enhance the car's overall performance. Throughout the design and testing process, we identify inaccuracy in our algorithm for calculating the average angle of the lane, recognizing the significance of precise calculation. We diligently improved the algorithm, resulting in expectational servo control and more accurate lane following. Lastly, we encountered an issue with our motor, which sustained damage from frequent stop and restarting. The accumulation of excessive heat within the motor led to irreversible damage. Consequently, after each round, we were required to restart the car entirely. Through preservation and innovation, we successfully addressed this obstacle and continuously improved the performance of our autonomous racing car.
That's how we overcome the issues. And now I'm going to hand it to Archie to talk about the further improvement.
Hi, I'm Archie. I'm going to talk about how we further improve the car in hardware and software. Overall, our autonomous racing car has successfully achieved the crucial capability of indoor line following. However, there are several areas where further improvement can be implemented to enhance its performance. For hardware, we can replace the current motor with a more efficient one to get more precise speed control. We can also improve the power efficiency by ensuring more effective power dissipation from the PCB board, and add an extra source like power bank to supply power to JC Nano and OpenMV to ensure enough power is supplied to servo and motor. This will help us solve the PCB overheating problem, which improves the motor control. For software, our current line following is heavily based on the average angle calculated from the line detected by whole line transform. We can improve its performance by adding blob detection that improve the accuracy of line detection and better performance for complicated traffic situations. Besides the hardware and software for basic line following function, the two extra features, ultrasonic sensor and object detection, can also be improved to help the car to navigate through complicated traffic situations. In our current design, the ultrasonic sensor's reading is now stable and accurate. This can be improved by adding an Arduino to run the ultrasonic sensor and output the reading to the OpenMV. The object detection can also be improved by feeding more pictures to the OpenMV to study. That's all we are going to present in the video. Thanks for watching and have a good day.